Okay, so for this question, we have a piecewise function in three pieces and some limit questions. So let's take a look. So this first one here, limit as x goes to -4 from the left. See how that little minus sign up there is left? That would be this one from the left of -4. So what do? So we take the function 3 over x plus 7 and we plug in -4. And you might wonder, you might say, well, Mr. Aaron, it's not equal to -4. So how can you plug in -4? Well, it's true, it's not equal to -4, but it's infinitesimally close, right? It's for all values less than -4, even those infinitesimally close, like -4.0000001, you know? And so that's good enough for the limit, because a limit is not the actual value you end up on, but it's what you're headed towards. It's what you get infinitely close to. That's what a limit is. So it gets infinitely close. When x gets infinitely close to -4, I can find out the value this function gets infinitely close to. 3 over 3, 1. So that's the answer 1 there. Okay. Now, when it's actually at -4, it's just -45. So that's right here. The actual value at -4 is -45. And then the final case is down here. This is to the right, which is this one to the right, greater than -4. See the little plus sign there. So greater to the right of -4. So then we take the function -11 over x minus 7, and we're gonna plug in again the -4 because it's infinitesimally close to it. And that's what a limit is about, what you get infinitesimally close to. So notice we have double negative here, right? Negative here, negative here, negative here, negative here. So +1, +1. So this is 1, 1, -45. So we choose, they're defined, but they're not all equal, right? They're not all the same. If you want to look at a graph, I don't want to use up too much time on this, but just a quick little, oh, that wasn't a very good line. That was too quick. I want to look at a graph at -4, 1, 2, 3, 4, over here at -4. The one from the left comes in at a height of 1, puts open dot. The one from the right comes in, does whatever, height of 1. But actually, the function itself is way down here at -45, solid dot at -45 height, where these are at a height of 1. So the function is going to have a discontinuity there, right? It's going to come in from this side, open dot, it's got to jump down here, jump out here. So you'd have to lift up your pen. That's discontinuous at -4. So it's discontinuous because they're not all equal. Okay, then it says list all the numbers of which it's discontinuous. Well, we've already seen it's discontinuous at -4. But what else? Well, anything that makes the denominator equal to 0 will make the function infinity, and therefore it can't be continuous because it goes up or down forever. So let's grab the one on the left, uh, this guy, 3 over x plus 7, and ask ourselves, what could we plug in for x right there to make that denominator 0? Of course, -7. Oops. -7 will make that denominator 0, which will make that thing equal infinity. So it's going to go up forever, and it can't be continuous there, right? Because this function back here at 4, 6, is it -5, -6, -7? This function, doing it a little more accurately then, must go whoosh at -7 up to infinity. So it can't be continuous. And then afterwards at -8, if you plug in -8, it's back down at negatives down here, doing something else at, oops, that was -7, wasn't it? Yeah, -8, it's back down here. So it's doing other stuff. So it's discontinuous there. And then where else is it discontinuous? Take the other function and ask yourself, what makes its denominator 0? What could you plug into him? Well, regular 7 would make his denominator 0, and he'll do the same thing. This function Almost goes rocketing high up at 7. So it's discontinuous there. Now, another version you might see, let me give you another one. You might get one like this where oops, um, all three of these come out equal. That can happen. They're all coming out the same. In that case, you say they're all defined and equal. So it is then it would be continuous. That would be like instead of this dot being down here, it'd be, right there, and then it's continuous. It fills in the gap, and then you can just smoothly draw the function. You can trace the function without ever lifting up your pen. If they're all equal, if they're all the same, then equal, all defined and equal, then it would be continuous. And then the same thing here. How do you find where is it discontinuous then? Well, not at the main point, but it would be like what can you plug into that? Anything that you plug into the denominator, that'd be -7. And then how about the other denominator? What can you plug into that one? That'd be a +8, right? Those are the two values you could plug in. But at the main point at x equals 0, it is defined. It's continuous, but it's discontinuous at anything that makes a denominator 0. And so that's how we do that.